Hello, my wonderful group of Physics 30s. We are now on to Unit 4, Lesson 1. Pretty exciting stuff. Unit 4 is all about EMR, or electromagnetic radiation. You've probably heard of it before as light, although light we honestly think about what we can see in terms of the visible spectra, which is a very, very, very small part of the electromagnetic spectrum. Yeah, light in quotation marks. And realistically, it's more of a review of waves that we're looking at for the first bit. And then we're looking at Maxwell and EMR. So Maxwell's the fellow who kind of first thought up the existence of EMR as it is. So things that we want to look at when we're dealing with transverse waves. So transverse waves are the ones, if you remember from Physics 20, that look kind of like this. What we want to think about as we go through and see these transverse waves, what is the source of these waves? Source. People say vibrations. Absolutely. Vibration will start off a wave. So many different types of waves. They all start off with some sort of vibration. You got your voice that starts off with your voice box vibrating. You can send waves through a spring or a slinky like we did last year, and then your hand is the source vibration. Now that source vibration tells us a couple different things. The vibration tells us about the energy of the wave. And does anybody remember how we represent energy on this wave? Like, where would we see energy on the wave? If you're saying that energy and amplitude go hand in hand, you are absolutely correct. So energy is represented by the amplitude. And amplitude is from our equilibrium or resting position to the top of a crest or the bottom of a trough. So amplitude. Now you might be wondering to yourself, what's a crest and what's a trough? Well, crests go above and troughs, you remember, go below our equilibrium position. So vibrations tell us the energy of the wave. Anybody else remember what the vibrations do? They tell us the frequency of the wave. Actually, I should write that out a little bit differently. They also tell us, there we go, the frequency of the wave. And we use our voices an awful lot in Physics 20. So my voice box is the source vibration for the waves that are coming out of my mouth right now. So I could have a really low frequency, like ooh, like that, or I could have a really high frequency, ooh. It's the source, it's my voice box that's telling me what the wave is actually going to look like. Cool. So we got the source vibrations that tells us about the energy and the frequency. Other things that we look at here is how could we figure out what a wavelength is on this transverse wave? So wavelengths from a starting position, say the top of a crest, through every position, and then back to where we started. So in other words, from crest to crest, that would be one wavelength. Or I could potentially do from a trough to the bottom of the next trough. So that would be one wavelength. I'm going to need to change colors to the next one. Or I could say, I'm going to go from here, I'm going to go through every single position and end up over here. So all the way down, all the way up to the top, and then back to the original. That is also one wavelength. So many different ways to measure one wavelength. Cool. Last little thing that we're looking at here is which direction is the particle motion versus the wave motion? So the wave motion is going to be side to side. I might even say, let's use green for this one. I might say that the wave's motion is this way, right? So the wave's motion is parallel or horizontal, I should say, in the plane of the page. Which direction is any given particle going to be moving? It's just going to be vibrating up and down. So particle motion for these ones, particles are moving up and they're moving down. So perpendicular to the motion of the wave is what I'm getting at there. Cool. So there's a really, really, really quick review of some transverse wave stuff, some things that we've talked about with transverse waves. So a couple notes with this, still in the review section here. What property of a wave never ever changes? Once it leaves the source, I should say. It is the frequency, right? So it doesn't matter if it is, and do you remember these terms from Physics 20? What this is called, the bending of a wave as it passes from one medium to another. It's called refraction, and we'll deal with that quite a bit through this unit. So it doesn't matter if it's slowing down as it goes from one medium and bending as it goes from one medium to another. If it's 60 hertz before, it's going to be 60 hertz after. Also, it doesn't matter if we lose energy. So again, that's the idea of damping, which you can kind of see right there. So remember, large amplitude means large amount of energy. When we damp a wave, that means that it's losing its energy, and we'd see that amplitude get smaller. But again, it doesn't matter if it's 100 hertz before, it's 100 hertz after. Cool, so frequency of a true wave never, ever, ever changes after it leaves the source. You may also remember couple definitions, frequency and period. So frequency, we're talking about the source frequency here, and it is by definition cycles per second, and it's measured in hertz after Heinrich Hertz, which we actually finally get to talk about a little bit today. I know we mentioned him a little bit in Physics 20, but now we get to talk about this person, Heinrich Hertz, in Physics 30. Cool. And then period is the time for one cycle. And even in those definitions, right, cycles per second or time per cycle, we know that there's an inverse relationship, which leads us to our formula, frequency is equal to 1 divided by period, or period is equal to 1 divided by frequency. It is an inverse relationship. And then, of course, don't forget period is measured in seconds. Cool, so lots and lots of review here. Speed of a wave, one important thing to remember, the only real way to change the speed of a wave is to change its medium. And sort of on that note, if it's the same type of wave traveling through the same medium, it's going to travel at the same speed. So this is actually going to be kind of important for us for this unit, because we're going to be looking at EMR traveling through different substances and changing its speed. So EMR through air, or light through air, you probably remember travels at 3 × 10⁸ meters per second. Through water, not so much, right? And it doesn't matter if it's high frequency, low frequency, it's all the same speed as long as it's the same type of waves through the same type of medium. But you change that medium, you change the speed. This is a thing that doesn't work. Okay. We also remember from Physics 20 our universal wave equation, so trying to figure out the speed of a wave. So we got V is equal to frequency times wavelength, where F is the frequency, obviously, and lambda is the wavelength measured in meters. Big thing for us now, though, is if we're in a vacuum or in air, the speed of the light is actually given to us on our data sheet. It is 3.00 × 10⁸ meters per second, and it is also no longer called V anymore. It is now C. It's a very, very, very specific speed. So it's got its own variable C, 3 × 10⁸ or 300 million meters per second. It's pretty quick. Pretty quick. Okay, cool. So universal wave equation, hopefully we all remember that. Now, quiz yourself here. Put the video on pause, see if you can figure out the answer to these questions. I'm going to do the same. I'm going to pause it, write out my answers, and we'll see if we agree. Alrighty, so I've got my answers here. So wave is a transfer of energy from source to receiver. Oh, so I mentioned we've already gone through a couple of these. I should mention this, but some of them we haven't gone through yet, but still all things we need to know. Number 2, the material a wave travels through is the medium, or called the medium. The source of all waves is a vibration. The property, which is the energy of the wave, that's our amplitude. If the medium doesn't change, the speed doesn't change either. Number 6 is a bit of a tricky one. I bet you some people were a little bit funny with this. If the frequency is high, the wavelength is short, right? And this comes from our universal wave equation. So V is equal to frequency times wavelength. So I'm looking at frequency versus wavelength. So I separate those two. Frequency is equal to V over wavelength. So that looks like that is an inverse relationship. Frequency has an inverse relationship with the wavelength. So as the frequency increases, the wavelength decreases, but we use kind of funny terms for this. So the frequency is high. Lots of people might have said that the wavelength is low, but that's kind of true. I mean, that's what an inverse relationship means, but we don't really describe wavelengths as being low. So if the frequency is high, the wavelength is short. Or in other words, if I have a large frequency, I have a small wavelength. Might be an easy way to think about that. And then finally, question 7, which property of a wave never changes? Well, that's the frequency. Cool. So again, a bit of a review question. You've actually seen stuff that's really similar to this in Physics 20. It's just now we're using light. So the key is we're using light, and that means that we know the speed. It's c, it's 3 times 10 to the power of 8 meters per second. 3.00 technically, but I'm being lazy and just putting 3. Okay, so it says, for the light wave shown, determine the period of the source vibration and the time for the wave to travel 75 kilometers. So the period of the source vibration, let's look at that first. We don't really have a good way to get period. Like the only formula that we really have with period in it for waves is period is equal to 1 divided by frequency. So maybe we should figure out the frequency for part A, and then if I can use that frequency for part A, well then I can use that to, or if I can get that frequency, I can use that to figure out the period. So for part A, we want to do that. But even then, I know that I'm going to be using my universal wave equation, v is equal to frequency times wavelength. Got the speed, that's just the speed of light, 3 times 10 to the power of 8. I say just the speed of light, that's big. But the wavelength is something that's missing. So I know from here to here is 800 nanometers. So what we did in Physics 20 was we built a little equation for this. I'm going to highlight in a different color, highlight in green. So I got one wavelength in green, and then maybe I'll do the other one even in a different color. One wavelength in red. So one wavelength in green, one wavelength in red. That means 2 wavelengths. Cool, okay, so let's see what we can do from using 2 wavelengths. I know that 2 wavelengths is equal to 800 nanometers. So if I wanted 1 wavelength, oh, I just need to divide that by 2. I built an equation for that. So the wavelength is equal to 400 nanometers. I don't really want nanometers, right? We're going to be dealing with a ton of nanometers, a ton of really small stuff in this unit. What I actually want is regular meters. So what I'm going to do is I'm going to replace nano with 10 to the negative 9. So it is 400 times 10 to the negative 9 regular meters. Now you think about that, that's not at all proper scientific notation. But when we plug that into our calculator will understand. Cool. So back over to the left-hand side of the screen here, frequency must be equal to speed over wavelength. Cool, I know the speed, 3 times 10 to the power of 8 meters per second. And then wavelength, 400 times 10 to the negative 9 meters. We plug those numbers in and just put the video on pause if you need to. Plug the numbers in, 7.5 times 10 to the power of 14 hertz. Now just remembering what that means, 7.5 times 10 to the power of 14, that's 7.5 times 10 to the power of 14 cycles every single second of this wave. That's crazy, crazy fast. So we're expecting a period for this. Period is 1 divided by frequency, so 1 divided by 7.5 times 10 to the negative 14. It's not going to take a very long time for 1 cycle. I'm expecting a very, very extremely small number here. In fact, 1.33 times 10 to the negative, I believe, 14? No, even smaller. 10 to the negative 15 seconds for 1 cycle of that wave. That is tiny, 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 tiny. So there's part A, right? Using our universal wave equation and some of those ideas we haven't seen in a little while to figure out the period. Cool. Part B, let's check out part B here. The time for the wave to travel 75 kilometers. So I'm just going to go ahead and cut this off. Not going to need much space for this one, and to really drive it home, I'm going to use a different color. I'm going to use that color. So for part B, what type of motion does this wave travel in? Is it uniform or accelerated? Absolutely uniform, so we know that that is physics principle 0. The only way to really change the speed of it is to change the medium, and it's not changing the medium. It's not mentioning that at all. So if it's physics principle 0, the only formula that we really have is v is equal to d over t. We're looking for how much time it takes to travel 75 kilometers. So time must be equal to distance divided by speed. So it's 75 kilometers, or 75,000 meters, divided by 3 times 10 to the power of 8 meters per second. So when you plug in the numbers, take a second and plug in the numbers there. It's 2.5 times 10 to the power of 4 seconds, which is a very, 2.5 times 10 to the power, I forgot something important there, 10 to the power of negative 4 seconds, which is a very, very, very small amount of time. So light can travel here on the surface of our planet 75 kilometers in approximately a 10,000th of a second. That's crazy. That's so fast. Which in one of our future lessons here, we're going to figure out that's one of the reasons why it's so hard to actually measure the speed of light, is because it's so ridiculously fast. So part A was all about universal wave equations. It used some stuff that was measured in meters, like wavelengths, frequency, period, things like that, period measured in seconds. Whereas part B is dealing with actual distances and actual time that wave is traveling. So don't confuse wavelength with a distance. Don't confuse period with a particular amount of time. Cool. So hopefully a bit of a review, and I left myself some space to work and didn't use it. Okay, so on to the idea of electromagnetism. This is actually pretty cool. This is where things start to get pretty neat here. So 1860s, James Maxwell created 4 laws of electromagnetism, and in doing so, figured out the whole idea. Like unit 2 is electricity, unit 3 is magnetism, unit 4 is light or electromagnetic radiation. So clearly there's some links there. Maxwell is the first person to think about this, or at least first recorded person to think about this. So the distribution of electric charge is related to the net electric field it produces. Yeah, totally. The electric field begins and ends on point charges. We've already talked about that. You don't really need to know the formula that describes this for this course, but we know that electric fields begin and end on point charges. Cool. We know the diagram. We know that magnetic fields are continuous loops, closed loops, right? We learned that in unit 3. So from the north, they loop around and they close on the south. Again, you don't really need to know the formulas that deal with this. We also know, and this is a little bit of order, this is his 4th law, we know that a changing magnetic field can produce an electric field, and that's our whole idea of electromagnetic induction. We change the magnetic field and we produce electric current via an electric field. Cool. And again, there are some formulas to describe this, which you may or may not see later in your life. But magnetic fields, changing magnetic fields can produce electric fields. Right? Exactly the same thing we saw before. So maybe a bit of review here, why not? The magnet is moving this way. We're kind of looking at Lenz's law. Lenz's law. Lenz's law was always fight the motion, right? So if I need to fight this motion, I need a south pole here, therefore I need a north pole here. So thumb, again, left hand rule 2, my thumb should be pointing towards the left. My fingers should be going up and then into the page on top. So yeah, that's the thing that I'm doing. I'm making the current move, right? And if you figured this out with left hand rule number 2, you're good to go from last unit. But we are making those charges move by changing the magnetic field. Cool. So what Maxwell did was he kind of figured, well, shouldn't an electric field make a magnetic field then? Pretty much symmetrical with law number 4. And again, he came up with the math. The big idea is to figure this one out. Thing is, he had absolutely no evidence for this, right? So he started to think to himself, well, what if this law was true, right? No evidence, but what if it was true? And that what if is just such a powerful way to think about things. It's all the way back to like, it might be like grade 1 or grade 2 or something, when you have your little nephew being like, well, what if this happens? Why is that? What if? And you keep asking those questions can lead to fantastic things. So the electromagnetic waves, or EMR, essentially what we have is we have a changing electric field or an accelerating charge. That accelerating charge creates a changing magnetic field. And notice if the charge is going down and up, so parallel with in the plane of the page, down and up, left-hand rule number 1 says it should be going in and out of the page. And actually, I'm going to put the video on pause here, and I might get some pictures. All right, nice. So I've got a couple pictures in my hands right here. So the first picture that I'm going to look at is, and remember it is hand rule number 1. So what is my thumb on hand rule number 1? That's the motion of the charges, and my fingers are the magnetic field. So thumb, motion of the charge, fingers, magnetic field curled around it. So when I look at this one, let's shrink it down a little tiny bit here, and let's say that the electrons are going upwards. That means that my fingers over here are coming out of the page on this side, and I'd have a magnetic field that is going out of the page. Cool. Okay, let me erase this a little tiny bit here. Let's say that that charge is, oops, wrong thing that I want to do. That charge is accelerating downwards. So now it's flipped and the charge is moving downwards and accelerating downwards. Now my fingers on that side of the page are all of a sudden going into, you can't see that at all, I'll just do X's, into the page on this side as they wrap around. So I'd have into the page. Cool. So that's the first little chunk of that one. The second little chunk is the fingers that are on top and on bottom. So I've got this one up top here. So my thumb is, oh shoot, I grabbed the wrong pictures. Give me a split second here. All right, I don't know what I was thinking. I needed the same picture over and over and over again, so I just ditched those other ones off to the bottom. But the magnetic field, so let's say that we're working in green here. The magnetic field in the top is into the page. So let's see here, I need into the page for that particular one. There we go. So into the page over here, we're going to end up with an electric field, or my thumb that's pointing up. If it is out of the page, it's going to be pointing down. And then same thing over here. So that electric field, we use our thumb for that one. So if it's down, I'm going to end up with into the page. Shoot. Into the page on this side of my hand. And if it is, there we go, electric field upwards, it's going to be out of the page for our magnetic field over here. All right, I kind of rushed through that a little bit and kind of got a little bit flustered, and I still am because nothing's erasing the way that I want it to. But long story short, what Maxwell said is all we need to do is start with an accelerating charge. We know that that's going to create a changing magnetic field, but that changing magnetic field, so the accelerating charge creates the magnetic field. The magnetic field is going to create an electric field. The electric field is going to create a magnetic field. The changing magnetic field is going to create another changing electric field. This is a wave, right? This is the transfer of energy, both in terms of magnetic and electrical energy, transfer of energy from one place to another. And it all started off with that changing charge. So this diagram is actually kind of important to know for like diplomas and stuff. So understanding that if my changing electric field is in the plane of the page up and down, my changing magnetic field, let me grab a different felt pen here. So my changing electric field is in the plane of the page up and down. My changing magnetic field would be in and out of the page, right? Always at right angles to each other. And the magnetic field, the electric field, and the velocity all at 90 degrees to each other. Cool. I hope that made sense, even though I kind of blundered my way through it. So what Maxwell says, the key to EMR is an accelerating charge. So let's think about which one of these things could create EMR, or like light in quotation marks, so electromagnetic radiation. So rubbing a balloon with your hair and then moving it back and forth. Yes or no? Yes, this would create EMR, right? Because we know rubbing a balloon with your hair, well, that's charging by friction. The balloon's probably higher in the electrostatic series, going to heat up, going to take those electrons from your hair. The balloon's going to be negative, your hair is going to be positive. And then as soon as you move it back and forth, you have accelerating charges. So yes, you absolutely would create EMR. A proton moving north at a constant speed. Is there acceleration there? No acceleration means no EMR. So yes, EMR for the first one, no EMR for the second one. An electron smashes into your TV screen and comes to rest. Is there accelerating charges? Yes. So would you have EMR? Yes, and that's actually how TVs used to work. They used to speed up electrons and smash them into your screen, and it would give off visual light, visual EMR. Cool. So an electron moves in a circle at a constant 7.1 meters per second. This one's a little bit trickier. So we do have a constant speed, but is it still accelerating? Around in a circle over and over and over again? Absolutely. The magnitude of the velocity isn't changing, but the direction is changing. So this is AC for centripetal acceleration, but it's still accelerating. It's not equal to 0. So yes, EMR for this one. We would create EMR. Cool. So, like we said, Maxwell couldn't ever prove this. It's Heinrich Hertz that showed that this was actually the case. So what Heinrich Hertz actually did was he set up a thing, like a device, where he's generating a bunch of electricity, generating a big potential difference, and then he's essentially got a spark that goes back and forth across this little tiny gap that's right here. So a spark that goes back and forth, kind of like our Van de Graaff generator when we had a spark going from one place to another. So from the Van de Graaff to our hands, or the Van de Graaff to the big metal pokey thing that we had. But yeah, so that spark, that means that charges that are accelerating back and forth between, I'm really having a hard time with these felt pens here, accelerating back and forth between that little thing. So if we do have a charge that's accelerating back and forth between that little gap that's right there, that should be giving off EMR, so a changing magnetic and a changing electric field. Now, way across the room, he's got this metal ring on an insulated stand. So if we have a changing magnetic field, that's passing in and through that ring, we know that a changing magnetic field should induce moving charges, right? That was the last lesson in Unit 3. And what he actually saw was he saw the sparks jumping back and forth across that ring. So it was indeed, depending on which direction the magnetic field was at any point in time, creating a magnetic field that caused current to flow in that ring. So he verified the existence of EMR, the changing electric and magnetic field, which is pretty cool. And he got a unit named after him for it. I don't know if that's why he got the unit named after him, to be honest, but pretty amazing, right? Verifying the instance of the existence of EMR. Hertz called these radio waves, and obviously we still use that term today. Right, we definitely do. No, this isn't part of our curriculum, but a guy named Marconi was the first person to ever use this to send signals, which is pretty amazing. So just thinking about that for a split second, think about across first the English Channel and then across the Atlantic Ocean from Britain to Newfoundland. Say you wanted to send a message from Britain to Newfoundland before 1901. What would you have had to do? You'd have to write it on a piece of paper, you have to put it in the post, you have to send it on a boat, and it would take months to get there. After 1901, again, this is a huge game changer. After 1901, it's at the speed of light. So almost instant message all the way across the ocean. That is huge. Just, it's crazy. It's just revolutionized the way that people communicate. This demo, I would have loved to do this demo with you. Essentially what we have is we have Van de Graaff generator on one side of the classroom. We have a FM, actually no, I like to use an AM radio with a speaker, and it's actually set to static on the other side of the room, and I'm drawing the wrong type of antennas. Typically, AM antennas are loops of wire, so solenoids essentially. But anyways, what we would do is we'd have these little shocks. So we'd have that other thing that's on the pole, and we'd get these little shocks that go from one side to the other, and we can actually send our radio signals, and as they pass through the loop, we hear them on the radio on the other side. And we can even do this from one room into another room. We are creating radio signals just by having those accelerating charges, just by having those sparks, which is really cool. Again, I'd love to show you that, but well, the situation we're in prevents it. Other applications of this are wireless charging, and obviously pretty much anything with communication, realistically, communication through the air. Okay, electromagnetic spectrum. So Hertz studied radio waves. He discovered that they have all the exact same properties of visible light. They are literally the same thing as visible light, just with a different frequency and a different wavelength. So they reflect the same way. So the top one is reflecting, and we will talk a whole bunch about reflecting. They refract, and we will talk a whole bunch about refraction. So it's the bending or the changing of speed as it goes from one medium to another. And then they also diffract. So that's the bending and the spreading out of the wave as they pass through an opening or around a corner. And they also all travel at the exact same speed, the speed of light. So all of the same properties as visible light, which is crazy. And then as people did more and more and more experiments with this, they figured out that every little piece of this electromagnetic spectrum is essentially exactly the same, from radio waves, microwave, infrared, visible, ultraviolet, X-ray, and gamma rays. So from the biggest thing, the size like kilometers long, the size of buildings, to the smallest wavelengths are the size of like nuclei, like tiny, 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 tiny wavelengths. They all do essentially and behave essentially the same thing. I shouldn't say they all do the same thing. We'll talk about that as we move through this in next unit, mostly next unit. But they all, for the most part, behave the same way. They're all changing magnetic fields and changing electric fields. It's wild. It's pretty crazy. Okay, so you do need to know the order of the electromagnetic spectrum. This is cute. You can say red Martians invade Venus using X-ray guns. So red for radio, Martians for microwave, invade for infrared, Venus for visible, or V for visible. There we go. Ultraviolet, so U for ultraviolet. X-rays, kind of an easy one. X for X-ray. And then G for gamma. So red Martians invade Venus using X-ray guns. Also, you could say raging Martians invade Venus using X-ray guns. Same sort of idea. The other thing that you need to know about for this is we need to know what happens to both the wavelength and the frequency as we go from one to another. So let's see here. Let's start with our frequency increases as we move down. So red has the lowest frequency, whereas gamma has the highest frequency. We also need to know the wavelength, and we already kind of talked about this. You know that they are inverse relationships. So what that means is wavelength increases as frequency decreases. So gamma has the highest frequency, it's got the shortest wavelength. So you do absolutely 100% need to know about these pieces. And then of course visible, the one that is special to all of us because it's what we see, it's what we interact with every single day, is sort of right in the middle there, and actually a very, very small part of it. Cool. So similar, same stuff that we just talked about. They all travel at the speed of light as a nice reminder, and that's it for today, folks. So enjoy our first lesson of Unit 4. Unit 4 is pretty cool. Unit 5 is very cool. Anyways, I'll stop talking now. See you again soon, Physics 20s, or Physics 30s. This is 30. Geez. Bye for now.